In this lecture we will be talking about oscillatory behavior for displayed by second order autonomous systems. Okay. So again, as usual, we will have some basic definitions and then we'll talk about implications of those definitions, or what types of conditions imply those definitions. Okay. Now we're all more or less familiar with the oscillatory behavior, and oscillation is the, in our context, is the phenomenon displayed by systems that possess a periodic solution, okay, a non-trivial periodic solution, possess a non-trivial periodic solution. By non-trivial we mean non-constant, because a constant solution, for instance a solution that starts at an equilibrium point, is periodic with any period, but we're not interested in that boring case. Okay? So we need something to be changing, for our definition of periodic solution. Okay? So by non-trivial we mean non-constant. So xt plus t equals xt for all t greater than equal to 0. And here, this constant, positive number, is what we're calling the period. Okay. And then, as for the visual counterpart of the definition, the image of a periodic solution in the phase portrait is closed trajectory. Okay. By closed trajectory we mean something like this. It closes on itself. Okay. Basically we're talking about a loop. Closed trajectory, which is called a periodic orbit. Or a closed orbit. Okay. So those are our basic definitions. Now let's apply those definitions, or see those definitions manifest themselves on some simple examples that we can visualize. Okay, some more or less. So let's visit again, because it's usually a good idea to try to apply a definition on a linear system first, if it's possible. Okay. If not, then you go on to, and later on you move on to a little bit more complicated phenomenon, okay, or dynamics, the nonlinear dynamics. Okay. But if there's an example to any definition with an LTI system, it's always good to study that first, because we know a lot about linear systems, and our understanding may help us to extend our grasp to nonlinear dynamics, nonlinear phenomena. Okay, so the example is linear, and it's a very famous system called harmonic oscillator. And this model, the model of harmonic oscillator, appears everywhere throughout nature and also applications. It's been used to model many things, and one of those things is the one that we're familiar with: mass attached to a spring. Okay. We have a linear spring. One end of it is attached to the wall, let's say, and then the other is attached to a block with mass M, and K is the spring constant. Now, what we found here is that if you just stretch the spring a little bit and then leave mass, what's going to happen is mass will oscillate back and forth if the friction is not enormous. If the friction is, and we build friction, eventually this will converge to a stop. Okay? But if the friction is very, very small, if this surface is very well lubricated or very smooth, then the oscillations will go on for quite a long time. Okay? And for the purpose of analysis, we can suppose that the oscillations will move on forever. That is, we can consider the frictionless case. In that situation, we obtain the so-called harmonic oscillator model. Okay. Linear frictionless mass spring system. Where the model directly comes from Newton's law and Hooke's law together, and y double dot. Okay. Y is the displacement of the block from the equilibrium position. Okay. This equals the force acting on the block, and the force acting on the block is the force due to spring, and that force is always is negative. It's always if you stretch the spring, then it pushes you back. If you it pulls you back. If you push the spring, it pushes you back. So it's always in the opposite direction. Therefore, my double dot equals minus ky. Okay, so let's collect all the y terms on one side. And if you do that, what you have is my double dot plus ky equals 0. Okay, so this is the model of mass spring system without friction. Now let's put this into our notation. For that, note that this is second order homogeneous differential equation. Therefore, by choosing two states, x1 and x2, we can put it into our x equals f of x format. Okay. And the system will be second order because we have a double differentiation. That's the highest order term. So let's choose, as usual, the states as physically meaningful variables, and physically meaningful variables in this case are position and rate of change of position, namely velocity. So x1 be, let x1 be the position of the block, and the second state be velocity. Okay. Now with this choice of state, we have the state equation x1 dot equals x2 and x2 dot, which is y double dot, equals minus k over n y, and y is x1, therefore x2 dot is minus k over n x1. Okay, so this is the state space representation of frictionless mass spring system. Okay, now to obtain the trajectories of the system, let's use some physical help or physical intuition, because there's no friction, and friction is the only mechanism where the total energy can leak out of the system. So let's try to analyze the system from the energy point of view. So what I mean is the following. First of all, let's write down the energy, the total energy of the system. And by total energy, we mean the energy stored in the spring at any given time, plus the kinetic energy of the mass. Okay, so E therefore equals potential energy plus kinetic energy. Okay, this is the energy stored in the spring, and that's the energy stored in the mass. Okay, and then let's write them down using high school physics. So therefore E is a function of y and y dot, or in our new notation in terms of x1 and x2. So E therefore is a function of the state vector x, and E of x is 1/2 k y squared. That's the energy stored in the spring, plus 1/2 m y dot squared. That's the kinetic energy of the block. And y dot was x2, therefore it's 1/2 m x2 squared. Some those, note that these are never negative, okay, and generally positive. Sum is therefore also never negative. And sum is what we call the total energy of the system. Okay. Now, in order to understand the behavior of this system, even though we have a good guess of the behavior of the system, is to look, or qualitative behavior of the system is to analyze it through the total energy, okay, by which I mean the following. Let's try to see what happens to the total energy of the system as time goes on, okay. So E is a function of the state, okay, and then as time goes on, the state changes, which we call a solution. Therefore, this E is also a function of time. Okay, if you replace this x with x of t in the solution. And what's E dot? E dot is time derivative of E dot is d over dt of E of x of t. 1/2 k x1 of t squared, 1/2 and x2 t of squared. And x1 of t and x2 of t are the solutions for the individual states. And that solution is some solutions starting from some given initial condition. Okay. Now, regardless of that initial condition, this E dot equals something, and that something tells us a lot about the behavior of the system. Let's figure out what that something is, and everything we need is on the board already. It comes from the model. So, time derivative of this is k x1 x1 dot. Time derivative of this is n x2 x2 dot. Okay. Now we have x1 dot and x2 dot here in our system. So that equals k x1. What's x1 dot? x2 plus n x2 times x2 dot, and x2 dot is minus k over n x1. Okay. By the way, k and n, they are positive constants. And what happens here is something remarkable. Here we have k x1 x2, and then this n and that n, they will cancel out, and here we have minus k x1 x2. So for all solutions, that is, for any solution independent of the initial condition, E dot, the rate of change of energy, is always 0. Okay. Which is not surprising, and physically we were expecting that, because we're considering the friction in this case, and the friction is the only way that the energy can leak out of the system. If the system is frictionless, then the energy is trapped in the system. That means it can neither increase nor decrease. It must stay constant. Okay, and we have just obtained that E that equals 0. Energy is constant. So our conclusion is that E of x of t, the total energy of the system along the solutions of okay, is constant. Okay. So in particular, E of x of t, okay, energy at all future times must equal the energy that you started with, and that's the energy at the initial condition. Okay, E of x0. This is initial energy. Okay. Energy is conserved. And that energy is conserved, or that E that equals 0, in this case will give us exactly the trajectories from which we can obtain the phase portrait. Okay. So let's interpret or translate this observation, E of x of t equals some constant which we call the initial energy, to translate it to visual domain. Okay. This is our phase plane, okay, or x1, x2 plane. Suppose that we start from some point, okay, here, x0. Okay. And then, if you start at this point, now this point will give us a constant, and that constant is the total energy at the initial time, t equals 0. And now for all future times, E of xt, the total energy of the system, must equal that constant number, okay? And that equality, this function, E of x, equals some constant, gives us a set of points. And that set of points, they form together a trajectory, okay? So, so this is the energy, and now we equate that to constant, and this equals constant, gives us all possible pairs of x1, x2. And in this case, if k and n, they were equal, it would be just a perfect circle, okay? But since we consider general case, k and n, well, possibly different from one another, in that case, this equals a constant, defines an ellipsis, okay, a generalized circle. So, we were expecting something like this. Okay, it's not really a perfect ellipse, but anyway, it almost looks like an ellipse. Okay, so this is x0, and for all future times, for all future times, the trajectory must remain on that constant energy. And this is a periodic orbit. Okay, because it will always remain on that curve. And for this case, it's an ellipsis defined by 1/2 k x1 squared plus 1/2 m x2 squared equals the constant, which is the initial total energy of the system. Okay. And now how about the direction? Direction is, remember, all we have to do to determine direction is we have to remember the equations, okay, the dynamics, which was x1 dot, for instance, the first equation was x1 dot equals x. For instance, choose a test point, okay, a test point where x, okay, for instance, this point here where x1 is 0 and x2 is something positive, okay. In that case, since x1 dot equals that positive thing, if you start at that point, initially x1 should increase because its derivative is positive. x1 increasing means that if you start from that point, the projection of that point on the vertical axis must be going to the right. So that means that the direction, as time goes on, is clockwise. Okay. And this is just a solution starting from this particular initial condition. And since the system is linear, you scale it, you multiply this by 2, you obtain another solution. You multiply this by 0.75, you obtain another solution. And all those solutions together make up what we call the phase portrait. Okay, so let's squeeze the phase portrait here. So this immediately implies, thanks to that the system is linear, x1, x2, 0. Phase portrait, and all are rotating in clockwise direction. Phase portrait. Now, here is an important remark which points to an essential difference between a linear system, what can be displayed by a linear system, and what cannot be displayed by a linear system. Something that can be displayed only by a non-linear system. A non-linear system is the following. In general, a linear system, a linear time-invariant system, cannot have an isolated periodic orbit. Okay. And by an isolated periodic orbit, suppose that this is periodic orbit, and suppose that we try and figure out whether it's isolated or not. The definition of isolated is as follows. Around that periodic orbit, what you do is you put an envelope, let's say. Okay, so you squeeze it in a donut-like thing. Okay, and then you can make this, the thickness of that donut, as tiny as possible. Okay, well, as tiny as you wish. Okay, now if you reach to some tininess, but still it has some positive thickness, if within that region, this thing, the trajectory, is the only periodic orbit within that positive thickness torus, then that orbit, that periodic orbit is called isolated. Okay. Otherwise, that is, no matter how you squeeze this envelope around that orbit, if you can always find another periodic orbit that's within that donut, then in that case we say that that periodic orbit is not isolated. Okay. And clearly, well, almost clearly, linear systems cannot have isolated periodic orbits. The reason is the following. Suppose you have a periodic orbit, and suppose that you claim that that periodic orbit for the linear system is isolated. But since you take the periodic orbit, you can inflate it. You can multiply it with 1 plus epsilon, okay, this constant. And epsilon, suppose that epsilon is positive. And epsilon you can choose as tiny as you want. Multiply that solution by 1 plus epsilon, and that is still a solution because the system is LTI. Therefore, and since this epsilon is arbitrary, and it could be either positive or negative, no matter how tiny you choose the thickness of that donut, you can always fit in as many periodic orbits as you want within that envelope, if the system is linear. And so that means the linear systems cannot have isolated periodic orbit. However, nonlinear systems do have, some nonlinear systems do have isolated oscillations. Okay. An isolated periodic orbit is quite an interesting thing to study, and many people study it for many years. And because it's quite interesting, it has a special name. It's called the limit cycle in the literature. Okay? It's called the limit cycle. Okay. Now, from this simple argument here, we're convinced that to obtain a limit cycle, an example limit cycle, we cannot search in the linear domain. We have to move on. We have to go to the nonlinear region, okay, nonlinear domain. And one such system that displays isolated periodic orbit is something that we talked about already, namely the van der Pol oscillator. Okay. So, and you may have observed already that it has a periodic, it has a limit cycle. If you have simulated the van der Pol oscillator, remember that the files are on the web page. Okay, if you're interested, it would be a nice exercise to visualize what we're talking about here. Okay, and van der Pol oscillator does display limit cycle. Okay. So let's remember once again van der Pol oscillator. Now I'm gonna put the phase plane, the limit cycle, and also the phase portrait of the van der Pol oscillator. It's not obvious why the dynamics produce such a phase portrait. Excuse me. So that's why I'm advising you to go to the simulations. So the model for the van der Pol oscillator was such x1 dot equals x2 and x2 dot equals minus x1. So at this point we have, it's just like the harmonic oscillator. Okay, it's a linear system, but it has so-called a nonlinear damping. Okay, epsilon 1 minus x1 squared x2, and here epsilon is something positive. And depending on this epsilon, clearly the shape of the limit cycle changes. Now, how that limit cycle looks like is as follows. Something like that, more or less. And well, of course, for some value of epsilon, this I believe is for some small epsilon. If you increase further and further, it makes some the shape becomes more and more distorted. Okay, here it looks more or less uniform. And this is 0, and that's the direction. And so this is a solution, and a periodic solution. This loop, this is a loop, so that's a the trajectory closes on itself, closes on itself, and this guy, if you start anywhere on that periodic orbit, you keep moving in that direction. So this is the limit cycle. And if you're interested in the phase portrait, so this is just one of the solutions, okay? If you introduce other solutions, you obtain the phase portrait, and the phase portrait looks like the following. Again, this is our limit cycle. is x2. Now it turns out that this limit cycle is stable. That is, almost all the trajectories starting outside the limit cycle converges to the limit cycle. Okay. Now this system has, we figured out already, has a single equilibrium point, and that equilibrium point is the origin. So that means if you start at the origin, you stay at the origin for all times. But if you start close to the origin or somewhere inside that limit cycle, what happens is that you move outside away from the origin, and eventually, after a few rotations, you converge to the limit cycle. Okay, so that's the trajectory. If you start inside this area, if you start outside the area determined by the limit cycle, what happens is this time you move spiral inwards, okay, toward the origin, but you don't reach the origin. You get stuck at the or on the limit cycle. Okay. Once you stop somewhere here. Okay, I'll just start here. Go that direction and see the face. Now, returning to periodic orbits, now the question is, how can we determine whether a system possesses a periodic orbit or not? For linear systems, the check is straightforward. Of course, we're talking about a second order system here. For the linear time domain system, all you have to do is, you check the eigenvalues. If the system has a pair of purely imaginary, non-zero eigenvalues, then it must have a periodic solution, and that periodic solution cannot be a limit cycle, because the limit cycle by definition is an isolated periodic solution, and linear systems, they do not have isolated periodic orbits. Okay. Now for second order linear systems, x that equals ax x R2 periodic exists if and only if the eigenvalues of A are purely imaginary. Okay. It is lambda 1, 2 equals plus minus j omega, where omega is a real number different than 0. Now, how about the nonlinear case? For nonlinear case, which is generally the case that we cannot have if and only if conditions, it's very rare. We usually have sufficient conditions or necessary conditions. And here is a sufficient condition for a periodic orbit to exist for a nonlinear system. It's provided by two scientists, okay, Poincar and Bendix. For nonlinear systems, we have an only sufficient condition, and the set of sufficient conditions is as follows. Poincar, Bendix, okay. Now we're going to list certain conditions, and in the end, if those conditions are satisfied, it was claimed by these people that, and proven by those people that the system must have a periodic orbit. Whether that periodic orbit is a limit cycle or not, they don't touch that issue, but they only give sufficient conditions for the existence of periodic orbit. Okay, so now let's see those sufficient set of conditions. Consider the system 1. X that equals f of x. Okay, and we're talking about second order system. So x is in R2, and therefore x is in R2 and f is in that from R2 to R2. And assume that f is differentiable, that is, assume the Jacobian exists. Okay, which is a reasonable assumption for many situations. And suppose that for that system, we find a subset, a domain of the plane, real plane R2, and it satisfies certain properties, which we will list now. Let N, a subset of R2, okay, subset, not subspace, be a closed and bounded subset of the plane. By plane we mean R2, and satisfies the following conditions. 1. N is free of Coulomb points so there are no Coulomb points inside N, or there might exist only one of them, okay, one equilibrium, but if there exists such an equilibrium, the Jacobian at that point must satisfy certain properties. Okay, N is free of Coulomb points, or contains a single point, let's call it X EQ, where Jacobian the 2x2 matrix evaluated at that particular equilibrium has both its eigenvalues with strictly positive real parts. Okay. So that's one condition, and the second condition is that N is forward invariant, okay, with respect to the system x equals f of x. Now, what we mean by forward invariant? We mean the following: every trajectory starting in N stays in N for all future time. Okay, so that means let's rewrite that sentence or re-express that sentence. That means if you choose the initial condition belonging to that subset N, automatically you have x of t belongs to N for all future time, for all t. Okay. Then, if this is the case, then such a subset is called forward invariant with respect to the system. Okay. Then N is said to be forward invariant with respect to the system x equals f of x. Okay. And then if these two conditions are satisfied, here is the result or the statement of the theorem, then it's just a simple then. It's not then and only then. Okay, so this is just a sufficient condition. Then M contains at least one periodic order. Of the system. Okay, so that's the statement of the theorem. We will not prove this theorem, but apply it. To understand it a little bit better, we will apply it on some particular example. Okay. So, before we close this lecture, let's go over the Poincare-Bendixson theorem once again. So we have a second order autonomous system, x that equals f of x, and we're interested in figuring out whether this system displays any periodic orbits, okay, or any oscillations. Well, one way is just obtain the write-down solution explicitly, and then look whether the solutions are periodic or not. But the problem with that approach is that, in general, we cannot figure out explicitly or exactly the solutions of nonlinear systems. Therefore, we have to search for indirect methods, and this is one of, or the most famous indirect method for hunting periodic orbits. Okay. And it says the following: suppose that this is our phase plane. Okay, x1, x2. This system is x that equals f of x. Now, suppose that for this system, you have some candidate subset of R2. Okay. Let this be M. Okay, what's inside this thing is what we're calling M. It must be closed. Okay. And bounded. Okay. So bounded means you can find a circle large enough so that it contains, or a disk that's large enough that it contains this M. So that's what we mean by a bounded subset. Okay. And then you concentrate on that subset. If, first of all, you check for equilibrium points. If the system has no equilibrium points inside M, then the first condition is satisfied. Okay? It may have some equilibrium points. It may have an equilibrium point here. It may have an equilibrium point here, but no equilibrium point inside M satisfies the first condition. Or you may still have an equilibrium point, but just one. One is allowed. No 2, 3. Okay, just one is allowed. And if you have such an equilibrium point, you have to check for the linearization. Okay, you linearize your nonlinear system at that equilibrium point. You obtain the A matrix. Okay, at that equilibrium point, X equilibrium, and the eigenvalues of the A matrix, lambda I, okay, must be strictly positive. Okay, for both eigenvalues, 1 and 2. Okay, so either no equilibrium point, or if you have an equilibrium point, this condition must be satisfied. In that case, the first condition is satisfied. And the second condition is the following. The second condition is such that if you choose any initial condition inside M, and then you start the trajectory, you start from that point, and for all future times, okay, that trajectory will remain in M, will never go outside M. Okay, you start another one here, and so on, but it never leaves M. Such an M is called forward invariant. That means it's a very simple definition. You start in M at any time, and you stay in M for all future times. Okay. If, for instance, the border of M is has a well expression. Okay, if you can nicely write it down, but it means, or geometrics, it means that If you start inside M, you can never leave M. So that means at any point, okay, at any point on the border, the velocity, okay, x dot, cannot be pointing outside M. It should always be pointing inside, or perhaps it's a tangent to M. Because if it's pointing out, so that means from that point, such trajectory can leave M, even for momentarily. Okay. So if it is forward invariant and if the first condition is satisfied, then Poincare and Bennigsen prove that then M must contain at least one periodic orbit, okay, of the system x equals f of x. Now, next lecture we will apply the theorem to a nice but simple example.